Am I live? Can you all hear me? Can I hear myself? This is usually the most nerve wracking part where I'm making sure I'm live. I think you all can hear me. I can hear myself. So that's a good sign. Hey everyone, welcome back to the study group. I was traveling last week, so for me as well, it's great to be back in the Chai studio. I'm excited to learn more and help you with everyone. Hey Les, great to see you again. I think Les was here last week as well. Thanks for everyone who's saying yes. Yeah, I was just making sure I'm live. So the goal for today's study group is to keep going in order of the chapters. I see an absolute expert in deep learning in the chat, and I have no idea why Jono is in the chat. But shout out to Jono. If you don't know him, find him on Twitter. He's one of the smartest people in deep learning. Look him up on Twitter if you can. Highly recommend that. Bob says hello. Cooper is saying they're still revising the previous week's video. That's awesome. You're still welcome to join, and I'll try to keep reminding you all of the concepts. Hey, Pastor. Hey, Praveen. All right. So for today, I'll keep going in order, and the agenda is to cover the third chapter, specifically the third notebook, which teaches you what is inside a transformer. So inside the book, they tell you the different parts inside of a transformer architecture. What is an encoder? What is a decoder? Why do you need the key, query, and values, and how do they work? And they step by step build up to an complete transformer model. I was also hoping to cover the next chapter, but I think I'll focus on this one and we'll go back to reading a few more papers and stuff around that. One thing I'll point out, I have been preparing a lot of questions for this book and for the reading group. So my plan is to publish them in the community forums. If you all could head over there and sign up, I'll publish them sometime next week. All of you are welcome to start discussions there, post stuff. Just sign up and head over to general discussions or introductions. Sometime next week, I'll release these questions. I have found that questions are a great way to learn, and this book was somewhat missing that. Nothing against the authors, but I think if you have the time and if you have the energy to learn such questions like why does attention work, what is attention versus self attention, why do you need to scale the dot products, we'll learn all of this, but we'll be looking at all of this stuff, and I'll be releasing these questions sometime next week. So you can check out the forums, you can sign up on the community forums if you like. I'll publish them there. The agenda is to again cover a few more things. So last week I had pointed out this notebook by Jeremy Howard. We'll revisit that. I'll do a more step by step walkthrough, and then we'll take a look at this notebook, which is titled Iterate Like a Grandmaster. It was in this competition where Jeremy had taught in this notebook how you can approach basically any problem and how you can iterate on your pipeline in NLP. So we'll take a look at that apart from the transformer anatomy walkthrough. One thing I'll start with, last week I had done a very quick overview of what named entity recognition is. So I'll switch back to that and we'll pick things up again from there. Before that, a quick recap. So we did a kickoff session with Lewis. We learned about what sequence to sequence models are. We'll revisit these throughout these weeks. Everyone, I'll keep revisiting concepts and keep pointing out different resources. I found that's the best way for me to learn. If you don't like that, or if you find there's a better way, I'm always open to suggestions. Hey Surya, Ranjan, Akshay. I'm recognizing a lot of names from the last study group, so that's awesome that everyone's still rejoining. All right, let me switch sharing screens and pick things up from the named entity recognition. I'm being distracted by the chat, so I'll try to only look now and then. Dylan is asking, is there a specific subsection? Right now, there is not because I didn't feel like a need for it. But if you want, you can start a discussion anywhere. Feel free for whatever you like. Just go in that flow. I'll have to ban Ayushman from the chat. It feels like. I'm pretty sure you're not drinking chai on a coffee on a Saturday evening, Ayushman. Let's be honest. Okay, so let's take a look at what named entity recognition is, and I'll use Hydrogen Torch, which is a um, end-to-end deep learning tool. This is a product that has been created by grandmasters, so we'll of course take a look at how you can do that through the Hugging Face API. But of course this will give you very SOTA results. The goal is to just use this as a form of an introduction to it. So what I've done is I've already loaded up the dataset in here, a data set for named entity recognition, and I can view all of my data sets here. So this one says text token classification, and this is sequence to sequence, and I can load up my data sets to different networks. So let's see if I want to start with another one, or we can probably just continue the text token one. I think we can continue the text token one itself. So what I'll do is I'll create an experiment with the dataset I've already loaded, which involves classifying the tokens, and it correctly identifies it as a text token classification problem. I can change different settings and work from there, but usually the default settings are pretty good. It's figured out that the label columns are NER tags, and it's going to use the entire data. If I wanted to speed things up, I can only select a portion of it. I can use the slider for that. We'll take a look at in the later half of the study group, but usually it's a good idea to also be aware of, is using lowercase a good idea or not. So I'll of course be looking at a lot of Kaggle competitions later on, but the thing worth looking at is, let's say if you're working with code cells, so let's say you're working with Python, in there converting everything to small case might or might not be helpful, and you need to be aware of what different architectures are and how they also behave with these. So we'll keep coming back to these concepts and looking at that. What is this Kaggle thing I keep mentioning? It's a website that's too basic for you, Jono. So you're already ahead of us grandmasters. I think Ayushman will write a fancy reply to what is Kaggle, because he's definitely drinking coffee. Um, cool. So you should ideally experiment with this. We looked at what max length is, and that is the number of tokens you can feed into. You would like to feed to the model. We also looked at why you should pad, or when and how does padding work while you're working with inputs to models. And from here, we can decide what pre-trained model we want to use. For the case of this quick walkthrough, I'll just use a bird pace model. And what I'll do next is I'll just run the experiment and I'll let it do its thing. I think I ran an experiment already. So let me jump to the older one. And you can see here, hydrogen torch makes it really easy. But this is what I wanted to point out inside named entity recognition. So it's correctly identified this as a person. Mexican is being identified as miscellaneous. I think that also depends on the data set. And I don't think this one has the correct labels, maybe. Or we could, of course, always fine tune this model further. It does identify US as the location, but not Mexican as the correct location. So let's take a look at the worst samples and the best samples. So in the best samples, we can take a look at where it's doing really well, where it's performing really well. And if I go to the worst samples, we can say that it's usually way off, and the labels aren't usually ideal. You can see that it's identifying a bracket here as a person as well, and bread is miscellaneous. It's also identifying stop words like the as miscellaneous. So all of this is really helpful in iterating upon what you're working on and taking a look at how the model is behaving. Maybe you want to switch the backbone, maybe you want to do some pre-processing. But what you're trying to achieve with named entity recognition is you're trying to tag words throughout the sentence and figure out what they are pointing to. And why is that helpful? That A, first of all, helps your model understand the context of things. And then also, when you're trying to summarize things, or when you're trying to um, perform question Q&A with the model specifically, that's also really helpful. So let's say you ask who is having chai, and then the model will figure out that Sanyam is a person who's having chai, and it'll give you that answer back. So these are also relevant, and we'll again revisit this topic again. But Just to point out, this is what named entity recognition is. I just trained this model really quickly in hydrogen torch, and if you want to learn more about this tool, you can check check out the website and find more details on H2AI's website. But for the purpose of today, I just wanted to point out how you can train a named entity recognition model. All right, let me switch sharing screen again and close some tabs. Kaggle is the Bible for machine learning. Yeah, I have to allow Ayushman sometimes because he also codes in Microsoft Word. So people who code in Microsoft Word are allowed. Spacey also has Displacy. Let's look that up. Thanks for pointing this out, John. It looks cool. I saw the preview image. Let's see, view more. The preview image looked cool, but all right. Yeah, this is pretty cool. And oh, it also works for other languages. This is pretty cool. And we can see that this is a proposition, this is a verb, correctly identifying different parts of the speech. This is cool. Thanks for pointing this out, Jono. Cool. So, for the purposes of today, I'll start by revisiting sequence to sequence learning next. And I had written about this paper in a blog where I explained it in about a 4 minute read. So, I'll use that paper. As a reminder, any blogs or any links or any tools I end up using, I'll link them right under the like button. And if you don't see them now, you can see them after the live stream. One more thing, I had 3 books to give away. So I promised I'll announce them today. I'll give away the books to, first of all, those who don't have it and those that are the most active in the chat. And this also applies to people from the last live stream. So I'll probably do like a mix of that. You don't have to do anything, just keep spamming the chat. And I'll send a book your way. Doesn't everyone use MS Word for coding? I use Notepad. I don't like MS Word. Pastor is saying he had some problems trying to submit to the competition. Sure, we can take a look. If you could please drop the link to your notebook, I'll try to take a look. So let's understand this paper or understand the summary of this paper. And in this blog post, I had pointed out that sequence to sequence with neural networks was one of the pioneer papers. And this showed that neural networks can be used for end to end translation. What does that mean? This paper came out in 2014. And at that point, end to end meant you didn't have to do any manual handcrafting of any different things at all. So you could just throw in the input and you'd get the translated output. I'm just looking at the coffee comments in the chat. The paper demonstrated that a LSTM can be used with minimum assumptions. So at that time, I haven't read a lot of papers, only a few, but you had to like perform some form of weird pre-processing on the text data every time, and you had to also analyze it, and they would only work, different techniques would only work with different models, so you had to always be careful with that. And this proposed this encoder decoder architecture which showed the promise of neural machine translation. You will see this acronym a lot of time when reading papers, not the statistical one as much, but NMT means neural machine translation. And I don't know, maybe they'll also ask this in interview. So there's this an ML interview tip for you all. Again, one thing worth pointing out, there were no frameworks like TensorFlow or PyTorch at that time. So a lot of things in the paper they had mentioned were, this is a deep LSTM where it was just like 3 layers, but at that time it was a deep model. The task was to perform translation of a sequence from English to French. The DNN expected a fixed dimensionality, which was a limitation at that time. So the paper proposes two models or two networks, model or networks, however you want to look at that. The first one would act as an encoder. So it would take your input and map it to a fixed dimension vector. So you can see the model in this image is reading an input ABC and produces some output. The model stops making prediction after end of sentence token EOS is reached. And one thing worth pointing out, LSTM reads the input in reverse. This is really cool, worth pointing out, because when you're trying to do a translation, you want to minimize the short-term dependencies. So by reversing it, it helps the model understand the or having an understanding of how to do translation better. Yeah, if you drink chai, you might win the giveaway better. I'll catch up on the chart after I'm done reading this. The model, the second network or model acts as a decoder. So the fixed vector that this input LSTM had created, it takes this as an input and maps it to an output sequence. They say the model is tasked to predict the conditional probability of a target sequence given an input sequence generated from the last layer. So you take the sequence and then create this distribution of target sequences. So let's say you have the word chai, usually great things should appear around it, and if you have coffee, terrible words should appear around it. So I would have that LSTM trained, and it would provide you this probability distribution. If you haven't watched the reading group on deep learning, we really go into a lot of depth of how to understand these notations and interpret these jargons. So I'm quite comfortable with it, but that wasn't always the case. And if you find yourself being slow reading such notations, that's pretty normal. So the reason they use two LSTM, this spawned the encoder and decoder architecture because this allows training the LSTM on multiple language pairs simultaneously. And this continued over to this encoder and decoder architecture, which we'll just see. And there were some other details inside the paper, but for the purposes of discussion today, the main point is there's this encoder that takes a certain input and creates an embedding, a fixed dimension vector, which is an embedding. And then the decoder takes this embedding and gives you the output. And this is also the basis of how transformers today work. Although you have transformers that are just encoder based, just decoder based, some have both of those. So inside the chapter, the authors point out how they work as well. But this is an encoder and decoder architecture. And this works best for sequence to sequence learning, where you are going from one sequence of words to another. So the reason it's called sequence to sequence learning is because you're going from one language to another and you're doing translation. Families that are just based on encoders, and inside the book, they do point out this family. So let me head over to that chapter now. This is the overview of architectures that are either just based on encoders. So the ones in blue just work off of encoders. The ones in red just have a decoder, and the gray ones have both encoder and decoder. And if you're new to the different transformer models, this is a really good image to just have an overview. So anytime you're using a model or you're interacting with the Hugging Face Hub, just remember this hierarchy. BERT was the first paper that came out, and inside the book they have like paragraphs explaining different things, but with different. Let's say if you look at Roberta, it's called robust optimization of the BERT training. Different such techniques were applied. XLM added multilingual support. Deberta is the latest and greatest. Deberta V3 is the latest and greatest of just encoder based architectures. So for these, they have something known as bidirectional attention, which means they look at both the word just coming before and after the thing you care about. And for families based on decoder, They are known as casual or autoregressive. They do not have bidirectional attention. And inside the book, they have different examples of what these are good at. So some are just good at question answering, some are good at named entity recognition, for example. And these are the kinds of question I'll publish onto the forums. So that's what I pointed out earlier. So here's an overview of all the kind of transformer models you can expect. And now I will again revisit these two blog posts I had mentioned last week. So I'll start with JLMR's post called Visualizing a NMT Model. And the main goal here is to understand how attention works. So again, and you'll see me do this a lot of times. I'll keep mentioning or bringing up the point again and again. I'm just catching up on the chat and I still see some. Optimus Prime is the best Transformer. I agree. You don't like Starscream, Ayushman? So for sequence to sequence learning, this is what's happening exactly. You could think of this as another language. And again, thanks to JLMR for all of these visualizations. I'm only using his blog post, which I'll link under the like button. The green could be a input language, and this is fed into the model, which gives out the purple language. And these are really cool models. So you could have any language to any language translation, given that they are not low resource languages. What are low resource languages? That is another question I'll publish. But low resource languages have low number of training examples on the internet. Under the hood, the green input gets mapped to an encoder, which is then fed to a decoder, which gives the output. The encoder sends the context over to the decoder, which begins producing the output sequence by sequence. And then he shows an example of how this works with French to English, I believe. The context is a vector, an array of numbers. And this is in the case of recurrent neural networks. It basically points them to how you can learn these different concepts. And these are the word embeddings that they are trained on. And you can print these, and you can also do really cool things like if you subtract king minus man and add woman to that, you'll get a queen. So this is how word embeddings interact. And inside the blog, he explains what recurrent neural networks are. But for our purposes, I want to point out how attention works. So you'll see in different steps, we somewhat force the model with a weighted average. So give these different scores to different hidden states. The key thing here, again, worth understanding is when you're working with attention, there would sometimes be multiple hidden states or multiple representations uh, to help the model give weightage, which then is attention. After which you apply softmax and do some multiplication. But very simply, I'll use another blog here, which is by Distill Pub. And they have a very cool visualization here. If you see this visualization, inside different contexts or depending on the input and output, the model would give different weightage via attention. So it's just a weighted average, if I may, to different words. So, for example, in the book, they point out if it's talking about flies, it could be a house fly, it could be something else. But depending on the context or depending how you give weightage to, yeah, you're doing great so far, data science castnet. But it's to give weightage to different words and help the model understand the context or work better in different contexts. And that is achieved through three different things: it's query, key, and values. And those words are really well used. So if you look at the paper or if you read the paper, you'll understand how they work. Inside the book, they give an example of how you're supposed to buy ingredients for different dishes. And let's say you're at the supermarket, we're trying to buy, look at labels, and buy ingredients for a dish, and they give analogies of that. Okay, let me catch up on the chat now. Notepad is for editing images only. No, it's for coding as well. What would be a good technique for question answer task without context and just Q&A data set? You could try zero shot learning, or you could just try a pre-trained model if you haven't already. I'm assuming you might have. So, if there is some paper that has some good research that would help the project, how can I make use of that knowledge? Most of the times, people have a lot of extra fluffy jargon. It's just a good idea to see if there's an open source repo along it. And if it has the code, most of the times it's just a readme which says coming soon. If it has the code, I would just download that and run it and see if it helps. If you don't understand the notation, it's okay. I don't know where the Andrew came from. Knowing what to ignore in papers is the real skill. I agree with you, data science Castnet. But yeah, like what you really care about is the code, right? Like, so I would just like go to GitHub. That's why I really like papers with code. Just go to GitHub, see if it has a code file, see if it has examples. Sometimes they have code that works. Most of the times they don't have examples. If they have examples, you're sorted. On YouTube, look up how I read a paper. Yes, Yannick has an absolutely awesome channel, and I have watched this video. So I'll again link his channel as well after this live stream. Causal, not casual. Yes, you are right. I messed that spelling up. Thanks for that. Another pro tip is you can check the papers with code side. Yeah, that's what I said. Yeah, this word is very triggering to me. Flan T5 seems to be pretty good for zero shot Q&A. Thanks for pointing that out. Yeah, I don't know what paper this is, but I'm sure it came out of a terrible lab. Would you suggest fine tuning DaVinci to create domain specific models? Um, I'm chiming in, but I don't know. It's you. Most of the times, it's worth just running these experiments and seeing what works best. So I'll let data science Castnet also answer it, but that's what I like to do. Cool. So this is how attention works, and it gives this different weightage to things. The thing worth pointing out, if you look closely at this representation, nothing else is completely grayed out. This has the darkest blue line, but other lines also have a light blue shade to it. So what this is representing is this particular state or this particular word, let's say, that you're trying to generate would be given the maximum weightage here, and everything else would be given a low score. So all of these would add to one, and that's how attention works. But not all would be zero. You could have some that are zero. Usually it's like a continuous number for all of these. And inside the book, again, they have different examples of different words and how they fit in this context. So this is another revisitation to attention through this blog by DistillPub. And now let's take a look at the illustrated transformer, also by JLMer. So again, he points out how transformer translates languages. They have this encoder decoder architecture. And inside here, the encoder component is a stack of encoders. The paper stacks 6 of them on top of each other. Um, and he also points out there's nothing magical about this. You can experiment with the number. The decoding component is a stack of decoders of the same number. So you'd have mappings from the encoders going to the decoders. And the encoders are all identical in structure, but they do not share weights. And each one is broken down into 2 layers, which is self attention and feed forward neural network. The encoder's inputs first flow through self attention layer. a layer that helps the encoder look at other words as it encodes a specific word. The output are fed to a feed forward network. The exact same feed forward network is independently applied to each position. The decoder has both of these, but there is an attention layer that helps the decoder focus on relevant parts of the sentence. And you would have these connections between the encoder going to the decoder. Then he brings the tensors into the picture. We'll take a look at this when we're looking at the notebooks. I'll scroll past it. Self attention at a higher level. So he also uses, I think, Bertwiz package here, which is no, he uses tensor to tensor uh, package, I think, but it's a similar package for the purpose of this. You can see that different words have this weightage being tied into what could be the next word, and this is basically making the model pay attention to how the flow of the sentence is going on. And coming back to the three things I said earlier: queries, keys, and values. These three work together. They're simply matrices, and they help, or they are the ground basics of how these transformer model work, or how this attention thing works. So you would have the embedding inside the input, you would have the queries, the keys, and values. And the score is generated by doing a dot product between query and keys. And then you would also normalize these later on, because you always want the model to have zero mean and unit variance. And you should be always doing that throughout the layers. As we take a look at the annotated transformer here, you'll see that after every layer, there's a, let me find that. You'll see that there's a layer norm, and after that, you have a position wise fully forward neural network, and then again a layer norm. And this keeps repeating itself. So finally, we take a sum of all of these, and that is the self attention calculation. So, again, a very higher level overview. I like to do this a lot, where I just look at concepts and give a brief overview and then come back and take another look. And I also like to look at a lot of different resources. So I'll point all of these out. For me, I enjoy learning from all of them. You can just read any one of these. JLMR has the best, one of the best write-ups. You can also take a look at the Distill write-up. All of these are really good. But I just like to read all through all of them. I'm not suggesting you should. That's just my preference. So now moving on further, I'll again use another resource here, which is annotated PyTorch paper implementations by labml.ai. And inside these, we'll take a look at multi-headed attention. So as you can see here, this is really cool because they take all of these different paper implementations, and you have this side by side where you can see where they explain what's going on inside the code. So I just given a very high level overview of you have this encoder and decoder, and there's some form of weighted averaging being done by using these three things, which we don't know how they work, but they're queries, keys, and values, and they're somewhat relevant to how the real world meaning of them would happen. But now let's take a look at how the paper implementation was done, and let's see if we can connect the dots somehow. Is this font size good enough for everyone, or should I zoom in a bit? I'll just wait for the chart. No, I code in NumPy only. I don't use all of this, and mostly CUDA. I don't use high level frameworks. I like this too. I'm still waiting for you all. Is this font size good for everyone? Okay, thanks. There's a question by Jono. Do all encoders feed into the decoder or just the last encoder? No, all of them are interconnected. I'm not sure if there are exceptions, but at least for the examples I've seen. Cool. I'll continue with this. So inside this walkthrough, again, thanks to lab ml.a, and I'll link this under the like button afterwards. They point out how multi-headed attention is implemented inside the PyTorch repository. So you have your standard imports. You're using Torch, you're using the NN module, and they also use their open source tracker. It's cool. I looked at this earlier today, and I think it's a cool framework. So experiment with it if you like. So this module, they say, does a linear transformation and splits the vector into given number of heads for multi-head attention. This is used to transform key, query, and value vectors. So this is known as prepare for multi-head attention, and it's importing from NN module. Inside that, you initialize with the dimensions of the module. So I looked at this earlier, and later on I learned that d underscore anything is the notation they are using for dimension of model, dimension of keys, so on and so forth. So you have a linear layer to do a linear transformation, and then you initialize the number of heads, the dimension of vector in each head. After that, you have the forward pass. And if I didn't have this annotated walkthrough, I would have been confused. But they kindly point out that input has either of these two shapes. So when we do -1, we are doing like a reverse, or we are looking at, if you don't know slicing, -1 basically looks at the elements in reverse order. So it does this transformation where it takes the shape in reverse order. And we apply linear transformation to the last dimension and split it into the number of heads. After that, you perform a simple linear transform. And then again, you split the last dimension into heads. The output has the shape of sequence length, comma, batch size, heads, and dimension of the keys, or batch size, heads, and dimension of the models. So after this, there's the class multi-head attention, and this computes the scaled multi-head attention for given query, key, and value vectors. If you haven't looked at this definition earlier, this is how attention is defined. It has three parameters: query, key, and value, and it takes the softmax of this particular expression. That's how you calculate attention, and that's how we end up giving those weights. In simple terms, it finds keys that match the query and gets the value of those keys. So when I read this, that you're trying to find keys matching queries and returning values, I thought maybe this is just good enough for question and answering, or something like that. But inside the transformer model, when it's trying to perform different tasks, even let's say it's trying to perform translation, it's also still looking up what could be a translation of the word. So again, this doesn't really happen. You don't really teach the model what to learn. It's like built into the weights, and it's almost autonomous, and all of these layers learn different things by themselves. But that's one way of understanding it. So it's not just for question and answering. That is one of the ways of understanding it. Let's read this one first. In context of translation, is it common to have the same embedding size for different languages? Hmm, I think so. I don't think there's any reason for changing the embedding size. Yeah, even I'm curious about it. But I don't know, like for the purposes of my stuff, I would just trust PyTorch developers. Maybe there's like a reason for speeding up. Maybe like rewriting from scratch helps stuff. Data science Castnet is pointing out you have multiple attention heads that work in parallel, so they can learn different things. Thanks for pointing that out. Is there a reason for different implementation of multiple heads? They aren't differently implemented. So you have multiple heads, which give. So let me point this out. We looked at different embeddings, right? So you could have different embeddings sharing different representations. Let me find some logout, or I'll just. So let's say these are like the three states you're working with, and in one of them it's giving some translation in a particular format, let's say, and here's another one. But depending on the input, you would give different weightage to such representations, right? So that's why you have like different heads which like help you understand different parts or help the model pay attention to all the embeddings. I don't know if that made sense. Some people do it slightly differently. Uh, yeah, maybe we're all just showing off our implementations. Maybe Ayushman will re-implement it in CUDA or, or C++, or I don't know, some weird thing like that. Okay, back to this. So now we're taking a look at multi-head attention module. So we define this class, and I just told you that this is how we define the attention. Um, would you call this attention phrase, attention variable? Let's call it attention variable. In simple terms, again, it finds keys that matches the queries and gets the values. It uses dot product of query and key as the indicator of how matching they are. And then it takes a soft max scaled by 1 divided by square root of dimensions of k. This is done to avoid large values causing softmax to give very small gradients. I assume this is self-explanatory, so like I won't go into it. But if this doesn't make sense to you, let me know. Softmax is calculated along the axis of the sequence or time. So now inside the constructor, we take the number of heads. We take d underscore model, which is the number of features in query key and value vectors. So we initialize the number of features per head by dividing d underscore model. What was that? That was the number of features in query key and value. And we divide it by number of heads. So we take a full number from this or a whole number from this. If you put double slashes, it doesn't pass on the floating variable, it takes an integer. Then you have the number of heads, which we just copy over. And then we perform these transforms to query key and value for multi-head self-attention. So we had created prepare for multi-head self-attention, and now we'll store the query key and value pairs by passing all of these functions to it. Sorry, passing all of these values to it, not functions. From there, you take a softmax for attention along the time dimension of key, which would be the first dimension. Then you just pass the output through a linear layer, calculate the dropout, and scale the values before applying softmax. Finally, you can calculate the scores between queries and keys. And it's done like so. So you take a dot product of query dot key transpose, or this is a representation of, I believe, einsum. They also point out how the mask comes into this picture, but this was the part I wanted to highlight so far. So finally end up calculating the einsum. If you aren't familiar with the einsum notation, I think this is another fancy way of doing the representation, but you can look it up. It's fairly straightforward. And it's simply put a way of doing matrix multiplication. But you are just calculating the scores between the queries and keys. So this was another look at multi-head attention. And let me catch up with the chat again. C++ is overrated. I'll implement multi-head attention in assembly. Makes sense to me. Does transformer help with computer vision use cases? Absolutely it does. Swing transformer is one of the most popular frameworks being used in vision right now. There's also VIT, which is vision transformer. Let's see if I have them open somewhere. I'm sure these guys would have the annotated versions of those. I don't need to see all the tabs. Let me see if I can find that. There's MLP Mixer, which is MLP architecture for vision. VIT is Vision Transformer. So you're welcome to look at this. This was an insanely popular paper when it came out. It's called An Image is Worth 16 by 16 words, if you are not familiar with this. But as data science Castnet is saying in the chat, these are like really popular for vision tasks, and they, of course, outperform CNNs until the recent CNN paper came out. I'm forgetting the name, which was an variation of ResNet. Does anyone remember the name of the latest CNN paper that showed very good results? I'm blanking out on that. I'll point it out if it comes to mind. I'm sure someone in the chat knows of it. Cool. So that was a look on another implementation of multi-headed attention. And I think we just might have the time to go through the book's implementation of it. So let's try to do that, and I will try to again revisit some concepts from last week by going through these notebooks. And inside the title, I had promised I'll yes, Connext was the one. Thanks. Connext V2 just came out. Thanks for that. This is a really cool paper. I'll again deviate a bit, but Connext is a really cool paper. It shows that if you like apply the techniques that transformers have learned to CNNs, and they do this like in a step by step fashion, you can also get really good results from them. Yeah, Ayushman, I meant that. Do you think transformers can be used for tabular data? There's another popular paper that I'll point out. RTDL. This is the paper. It's called Research on Tabular Deep Learning, and the package is RTDL. If you look up RTDL, it took me to this link. So I just looked up RTDL, and it took me to this page. But this implements a ResNet for tabular learning, and it like teaches you some trick of how to make it work really well. And it's also a package that you can pip install. So you can look at this example notebook and see if it's interesting to you. This was a really good read, so I would just encourage you to check this paper out. This is the only one I know of, and there's also Tabnet, which is fairly popular among Kagglers. This is more of a recent one. Can we use transformers for time series data? I've not seen good examples where it like outperformed other stuff. Maybe Tabnet. Dylan is saying Tabformer is a pretty interesting paper. I should bring back the paper reading group. I will probably soon. Once a week I'll read a paper, or like once every 2 weeks. Can transformers be used for transformers can be used for anything. You just need to try and see if it works. But I don't know about this, Sam. Any particular reason why transformers aren't as common in diffusion based image generation? I have seen some papers that involve uh, attention. So not the complete transformer architecture, not the exact encoder decoder representation, but I think I've seen some that have attention in there. I think it's just catching up. Maybe we'll see more of those. There's a package called Pythos Tabular. Let's look this up. Pythos Tabular. Data Science Castnet is saying bye bye. Thanks for joining. Aims to make deep learning with tabular data easy and accessible. Do they have examples? So you're working with Uh, Mixed classification, which is taking categories, features, and samples. This is a cool framework. I didn't know of this. I'll probably take a look at it and come back to it later. Maybe in the next live stream, I'll try to cover this if it's interesting. But this is cool. Thanks for pointing it out. Any financial based transformer models? Not that I know of. But I think Tabnet should work with financial data. You can try and see. Cool. So let's try to cover this. And if you're interested in the paper reading groups, consider subscribing because I'll also be live streaming them sometime. Or I'll try to make them as separate videos. I don't know if I'll live stream. We'll see. That should happen in a few weeks though. So here's a look at the transformer architecture from the book. You have time flies like an arrow, and I assume this is the German representation of it because I don't know German. But you have this text tokenized. What is tokenization? It's just taking the text and breaking it into individual words or subparts, subwords, or into individual characters, and then converting it into numbers. Because neural networks are matrix multiplications, and matrix multiplication only works with numbers, not words. So you have to create this representation and then convert back to it. After that, this is pretty cool. You have something known as a positional embedding. And inside the book, they point out this is how they stand out, such transformer models, that they also encode the positional information. And this is pretty important, right? You could just have this embedding which just gives a representation to the model. But positional encoding also passes on the information of where in the sentence does it appear and how important that is. So this is then passed on to the encoder stack, which then generates the key and value. From there, it's passed on to the decoder stack, which finally gives the output. So inside the encoder, you have multi-head attention, from where you have a lot of feed forward networks through which you're generating all of these outputs. And one thing worth pointing out, this representation does show that there are different inputs and all of these have different outputs going on to feed forward networks. So it's not the exact same matrix or vector, it's different vectors that are being fed through all of them. And just to point out, guys, I like it took me a long time to understand this notebook. I like spent 2 or 3 days through it. I'm sure you all are faster than me, but if this feels rushed, just like rewatch the video or run the code by yourself. It'll just take a while to wrap your head around it. But like this chapter is really good. So you have the tokenized text, which is fed into token encodings and embeddings. You add the positional embedding again, and from there you generate this hidden state. Self attention allows the model to look at different words and understand the context. So, does flying mean literally flying in the air, or does flying mean insect? So, you can see that this self attention is giving different colors to this vector, which means it's giving different weightage to different representations. Basically, some of these numbers would mean some different things to the model, right? Again, neural networks work with numbers, and to give weightage, you have these different colors showing the weightage, helping it understand what the context is. Dylan, it takes 15 minutes if you're reading Chai. I feel everyone out is out to get me today. They show BertWiz, which is a really cool visualization. So here, what they're doing is they're importing BertBase and creating a tokenizer, creating the model, passing on the text. Time flies like an arrow, and then they showcase how the model is interacting with different words and how the representations are connected to each other. So you can see time has this weightage which is being given the most to arrow. So I don't know if you all can see in the live stream, but the darkest blue arrow is towards air, and fly is also an arrow, right? So this is how the attention is working across different layers. You can take a look at different heads. So you could take a look at head 9, head 4, and you could look at different layers. This is a really cool package, by the way. I really like how it allows this. And you can see later in the layer the representation changes a lot, because that's where the position is being encoding. And again, we also looked at what SEP means, what CLS means. These are just different ways of telling the model that, hey, this is a separator, this could be a full stop or comma or something like that. Dylan says the visualization is clear. So that's good to know. So you can see that this is how the weightage is being given to these models. I'm pretty sure this is a very light shade, but you can see that even in the later layers where it's close to ending the sentence, there's still some weightage being given to the other words, right? And this is basically why you have all of these attention heads, and this is why these models are really memory intensive. To make them more robust, you definitely need a lot of representations, and later in the book they point out it's 768 by the batch size and by comma sequence length. That's how it's represented. So it's like if 5 is the sequence length, it would be 1 comma 5 comma 768, right? And you have all of these sequence lengths and all of these embeddings which basically eat up all your memory. Why do you need all of these representation or all of these vectors inside your memory? It's really hard to learn all of these contexts, and for the model to be able to by itself understand these concepts, do some translation, all those things by itself. That is why you have all of these representation, and that is why attention was the coolest concept, because it taught the model how to draw these lines and how to make it pay attention pun intended, between different things. So next they demystify queries, keys, and value, and how these behave, and they basically end up replicating all of the stages of the model. Cooper is asking why separator is dark blue, which shows important relationship. um that's a good question. Maybe in another head that's not the case. That is still the case. Time flies like an arrow. It looks like this model isn't Bert isn't doing well here. That's a great question, Cooper. I'm not sure about this. So in the last head, there's a different representation to it. I'll look this up and answer it in the next live stream. I don't think, Dylan, it's not a stop word, right? In this case, it's just before arrow. You might be right though. And here arrow points to separator. Hmm. I don't know if anyone has a better answer, but I'll try to answer this by next week. Okay, so yeah, even Dylan is confused now. Okay, so I wanted to cover this entire notebook, but we're coming up on the hour, and I really want to try not to go over it. So I'll give a high level overview and we'll revisit this again next week. So inside this notebook, the authors walk you through how the embedding layer is created, how the token embedding layer is created. From there, you get the input embeddings, and then you create the query, you initialize query with the same dimensions. You get the dimension of the keys. And this is the first time I learned about torch.bmm. So let me also point that out. The pop-up visible? I'm guessing it is. It performs a batch matrix product of matrices stored in input. I guess this is another way of doing multiplication, right? Like to the point being discussed earlier that you have all of these representations. Uh, this is another way of doing that. So after that, you pass the weights to a softmax layer, and then you create a scaled dot product attention function where you are calculating the dot product of attention and scaling it, which then gets passed through a concat layer and a linear layer. And then they iteratively build upon this. So they point out how you add a layer norm between different layers. They do that and they show the size is still the same. Then they create positional embeddings and teach you how to do that, how to add a classification head. And finally, we create the decoder and that completes the architecture. So again, I only highlighted different things. We'll pick things up from here next week. And I also wanted to point this notebook out, but we'll again come back to it next week. My focus is on making sure I explain these things clearly. I don't know if like this was helpful or not to you all, but if it is, I can just speed things up. If it's not, let me know. Did you get your jacket? I think he's asking Nishchay. No, he did not. Now is the time we are going to stretch a little, and that's understood by all. No, I think we can wrap up here. We'll meet again next week at the same time. I didn't get a chance to create the next live stream, so you all can subscribe if you want, and you'll be notified when that happens. It'll be at the same time. We'll continue from this notebook. I'll again wrap up this notebook, and then we'll take a look at the next chapter, which is multilingual named entity recognition, and we'll also learn how to submit to competitions and do that effectively. So for today's giveaway, Dylan, if you could please reach out to me anywhere with your email, I'll send a free copy of the book to you. It'll be a digital copy. I hope that's okay. And let's see. I think Ayushman was spamming a lot, so I'll send one to Ayushman as well. Cool. Ayushman and Dylan, please reach out to me to win the. If you're interested in claiming the book, if you all have one, I'll send it to someone else. Cool. Thanks for watching. We'll meet again next week, guys, and I'll hopefully in one go complete the attention walkthrough.